Good morning, everyone. So welcome back to school. Hope you had an enjoyable break. We're going to start this trimester where we left last trimester, and that is working with polynomials, in particular quadratic functions. So we'll be looking at chapter 6, but before I get into chapter 6, I'm going to have to review some things with you, just a couple things. Last trimester, we factored trinomials and we found the zeros. So let me review here. So for example, we had f of x is equal to x squared plus x minus 12. And to factor that, factors of x squared plus x minus 12 are x plus 4 times x minus 3. And then we found the zeros. We found where that quadratic crossed the x-axis. So we said x plus 4 is equal to 0. And we got x is equal to negative 4. And we set x minus 3 equal to 0. And we got x is equal to 3. So as you can see, my zeros were negative 4 and a positive 3. I want you to notice, though, that the zeros were negative 4 and a positive 3, but my factors actually were x plus 4 and x minus 3. It's kind of like you reverse the sign. We had a happy graph because the leading coefficient was positive. The leading coefficient was positive. So we had a happy graph. And then the last example we'll take a look at. Again, we have a quadratic f of x is equal to negative x squared plus 6x minus 8. I factored out the negative. And in factors of x squared minus 6x plus 8 are x minus 2 times x minus 4. And again, we found the zeros. X minus 2 is equal to 0, x is equal to 2. And then x minus 4 equals 0, x is equal to 4. So my zeros were 2 and 4, which we can see from the graph. 2 and 4. The leading coefficient was negative, so it was a sad graph. Okay, but again, I want you to notice that our zeros were x is equal to 2. My factor was x minus 2. My zero was x is equal to 4. My factor is x minus 4. Keep that in mind. Now, we looked at quadratics. Today, and for the rest of the chapter 6, we'll look at polynomials, but a quadratic function is a polynomial. So I'll define polynomial in just a second. So our objective today is to classify and graph polynomials. Some vocabulary terms: a monomial. A monomial is just one term. For example, 1 or negative 4x squared or 7x cubed. Those would all be considered monomials. A polynomial, well, we'll see what that is in just a second. And then the degree of a monomial. Well, let me work with these examples. The degree of 1, for example, the degree of 1 would be 0 because I could write 1 as 1 times x raised to 0. And the degree of minus 4x squared would be 2 because the exponent is 2. And then the degree of 7x cubed would be 3 because the exponent is 3. So how do we look at, or how do we define degree? Well, we take a look at the exponent for each of those terms. For 1, I had 1 times x raised to 0, so the degree is 0. For negative 4x squared, I had x raised to 2nd, so the degree is 2. And then 7x cubed, my exponent was 3, so my degree was 3. Okay, so that's what we mean by a degree of a monomial. We'll see what the degree of a polynomial is in just a second. And then leading coefficient we talked about a lot last trimester. We'll see what that is again. Binomial is just 2 terms. So for example, x plus 1 will be a binomial, or negative 2x squared plus x would be a binomial because we have 2 terms. Trinomial, again, 3 terms. So for example, x squared plus x minus 12. We just looked at that. And then a polynomial function. All right, so let's define the terms that I did not talk about or write anything about. So the degree of a polynomial is given by the term with the greatest degree. So for example, for x squared plus x minus 12, the degree of that polynomial would be 2 because 2 is the largest exponent I have. For negative 2x squared plus x, again, the degree would be 2 because 2 is the largest exponent I have. For x plus 1, the degree would be 1 because, again, 1 is the largest exponent I have. If I had just a binomial 7, the degree would be 0. Why? Because I could write 7 as 7 times x raised to 0. Anything raised to 0 is 1. So the degree of that polynomial would be 0. Oops, 0, not 1. All right, so a degree of a polynomial is given by the term with the greatest degree. A polynomial with one variable is in standard form when its terms are written in descending order by degree. So in standard form, the degree of the first term indicates the degree of the polynomial, and the leading coefficient is the coefficient of the first term. So here I have 5x cubed plus 8x squared plus 3x minus 17. The degree of 5x cubed is 3. The degree of 8x squared is 2. The degree of 3x is 1. Again, I could write 1. And the degree of negative 17 is 0 because I can write that negative 17 times x raised to 0. Well, that's the degree of each term. But the degree of the polynomial would be 3. So this polynomial, if I wrote it as a function, f of x equals 5x cubed plus 8x squared plus 3x minus 17, the degree of that polynomial would be 3. Okay. So the degree of the first term indicates the degree of the polynomial. Now, what's a polynomial? Well, a polynomial is just a collection of terms separated by plus or minus. So a monomial is a polynomial, one term. A binomial is a polynomial. A trinomial is a polynomial. Now, any polynomial with more than just 3 terms, we just say it's a polynomial. So let's look at this. A polynomial can be classified by the number of terms. For example, we have negative 9 here. Let me get my red. We have negative 9, and the degree of that polynomial would be 0. We have x minus 4, and the degree of that polynomial would be 1. We have x squared plus 3x minus 1, the degree of that polynomial would be 2. And then x cubed plus 2x squared plus x plus 1, the degree of that polynomial would be 3. Again, in standard form, you determine the degree of the polynomial by the exponent of the first term. For 2x to the 4th plus x cubed plus 3x squared plus 4x minus 1, the degree of that polynomial would be 4. And for 7x to the 5th plus x to the 4th minus x cubed plus 3x squared plus 2x minus 1, the degree of that polynomial would be 5. So again, the degree of a polynomial, the degree of the first term indicates the degree of the polynomial. And the leading coefficient is the coefficient of the first term. Okay, so here the leading coefficient was negative 9. For the first example, the leading coefficient was 1. For the second example, the leading coefficient was 1. For the third example, the leading coefficient was 1. Here, the leading coefficient is 2. And then the last one, the leading coefficient, is 7. And we can give each of these a name. So -9, that would just be constant. And then we have a linear, x minus 4. We have a quadratic, cubic, x cubed, and quartic, okay, meaning 4, and quintic, meaning 5. Okay, so for the quadratic x squared plus 3x minus 1, I could say is a quadratic trinomial. 3 terms, quadratic. For the cubic, I could say it's a cubic polynomial. Again, any polynomial with more than 3 terms, we just say it's a polynomial. So, and then the quartic, I could say it's a quartic polynomial. And then the quintic, I could say it's a quintic polynomial. If I had something like this here, 4x to the 4th plus 1, I would call that a quartic binomial. Quartic binomial. Quartic meaning degree 4, binomial meaning 2 terms. Or if I had -5x to the 3rd by itself, I would just call that a cubic monomial. Cubic monomial. Okay? So it's some of the terms that we can classify polynomial as. Now let's look at the graph of polynomial functions. Linear function, degree 1, it's just a straight line. Quadratic function, degree 2. Cubic function, one possibility for cubic function will look like that. It's degree 3. Quartic function, degree 4. And then quintic function, degree 5. Last trimester, we were concerned with finding the zeros of a quadratic. Now we'll be finding the zeros of higher degree polynomials. We'll be finding the zeros of cubics. So for example, some zeros I see here would, okay, here let me just, so for the quadratic, the 0 that I see there is just x is equal to 0. And so that could be, possibility would be y is equal to x squared would be the function. A 0 I see for the cubic would be, let's say, so x would equal probably like -2, and then x was equal 1 maybe, and then x is equal to 2. So those would be the zeros of that cubic function. So we'll be finding the zeros of polynomials just like we found the zeros of quadratics. More of that a little later. Okay, but before we actually get into writing polynomials, because that's one of the objectives today, let's see here. Classify and graph and write polynomials. Here, let's just do classify and graph and write polynomials. Okay, before we get into writing polynomials, we'll take a look at what's called the end behavior. The end behavior of a polynomial is a description of the values of the function as x approaches positive infinity or x approaches negative infinity. The degree and leading coefficient of a polynomial function determines its end behavior. It is helpful when you're graphing a polynomial function to know about the end behavior of a function. And I'll give you a very easy way to remember the end behavior of a polynomial. Let's look at a quadratic that's a happy graph. So y is equal to x squared. Okay, that graph always looks like that. The end behavior as x goes to, so if I wrote this on a coordinate plane, the end behavior as x goes to positive infinity, y increases. As x goes to negative infinity, y increases. So the end behavior of y is equal to x squared is that both ends increases as x goes to positive infinity and x goes to negative infinity. Just remember how x squared looks. And if I had y is equal to negative x squared, well, that would be a sad graph. So that would look something like that. The end behavior as x goes to positive infinity or as x goes to negative infinity, both ends decrease. They go down, y decreases. So remember what a quadratic looks like. So let's take a look here. And then the other graph that we should remember is a simple cubic function. So y is equal to x cubed. And we'll take a look at that. And that will kind of look like this here as we see the picture. As x goes to positive infinity, y increases. Y goes to positive infinity. So as x goes to positive infinity, p of x or y goes to positive infinity. And as x goes to negative infinity, y goes to negative infinity. So as x goes to negative infinity, y goes to negative infinity. So if the leading coefficient is greater than 0, a is greater than 0, in this case it's 1, it rises on the right and falls on the left. Okay, so just remember positive. So if it's positive, it rises on the right and falls on the left. For a quadratic, even degree, if it's even degree, as x goes to negative infinity, y goes to positive infinity. As x goes to positive infinity, y goes to positive infinity. It rises on both the left and right. If the polynomial is even degree and the leading coefficient is greater than 0. So this would be my function y is equal to x squared. Here's my function y is equal to x cubed. Right? And then if the leading coefficient is less than 0, as x goes to negative infinity, y goes to positive infinity. And then x goes to positive infinity, y goes to negative infinity. We say it falls on the right, rises on the left. That's for an odd degree. So this would be like y is equal to negative x cubed. Y is equal to negative x cubed. And then for a quadratic, if the leading coefficient is negative, as x goes to negative infinity, y goes to negative infinity. And as x goes to positive infinity, y goes to negative infinity. So it falls on both ends. So there's only really 2 graphs that you need to be concerned with. Actually 4. But 2 family of functions you need to be concerned with and remember. And you'll know everything about the end behavior. It's just y is equal to x squared, and whether or not the leading coefficient is positive or negative. If it's positive, it rises on both ends as x goes to positive or negative infinity. If the leading coefficient is negative, it falls on both ends as x goes to positive or negative infinity. And that would be the case for any even degree polynomial. Degree 2, degree 4, degree 6, degree 8, doesn't matter. Okay? And then the cubics. Y is equal to x cubed. Know what it looks like. Okay, as x goes to positive infinity, y goes to positive infinity. As x goes to negative infinity, y goes to negative infinity. And then if we had a negative leading coefficient, as x goes to negative infinity, y goes to positive infinity. And as x goes to positive infinity, y goes to negative infinity. And that would be the case for any odd degree polynomial. degree 3, degree 5, degree 7. It doesn't matter. So those are the ones you just need to remember. And you'll know everything about the end behavior of polynomials. So like I say, you only really need to remember two classes of functions, polynomials, x squared and x cubed. So let's take a look at some examples here. Okay, the determining end behavior of a polynomial function. Here, I see I have an even degree, 4. So it's either going to rise on both ends or it's going to fall on both ends. Well, here, because the leading coefficient is negative, I'll have a sad graph. Okay, so it will be that one. So as x goes to negative infinity, y will go to negative infinity, and as x goes to positive infinity, y will go to negative infinity. It falls on both ends. Let's look at the next example. 2x to the 5th plus 6x to the 4th minus x plus 4. It's an odd degree. It's an odd degree here. Okay, so what I remember is what x cubed looks like. X cubed looks like that. Okay, and it has a leading coefficient is 2 and it's positive. So that means it will rise on the right and fall on the left. So as x goes to negative infinity, y goes to negative infinity, and as x goes to positive infinity, y goes to positive infinity. Okay, let's look at some more examples. Identify whether the function graph has an odd or even degree and a positive or negative leading coefficient. Well, it doesn't look like a quadratic. It certainly doesn't look like an x squared, because an x squared rises on both ends, or it doesn't look like that. Or it falls on both ends, so it's not a quadratic. Okay. It's not degree. It can't be an even degree. Okay, but now let's take a look at odd degree. So again, if it's odd degree and the leading coefficient is positive, it's going to look like that. It rises on the right and falls on the left. Or if it's negative, if the leading coefficient is negative and it's odd degree, it will look like that. It will rise on the right, or rise on the left and fall. Rise on the left and fall on the right. So this one then has to be an odd degree polynomial whose leading coefficient is negative. So the LC has to be negative leading coefficient, and it's odd degree. Negative leading coefficient, odd degree. As x goes to negative infinity, y goes to positive infinity. As x goes to positive infinity, y goes to negative infinity. P of x is odd degree with a negative leading coefficient. Okay. This one here, well, that would be odd degree, and the leading coefficient would be negative. The leading coefficient would be negative. As x goes to negative infinity, y goes to positive infinity. As x goes to positive infinity, y goes to negative infinity. That's odd degree with a leading coefficient. So let's just take a look. What happened if I had a graph like this here? Well, it would be even degree. It would be even degree, but the leading coefficient would be negative. So it would be even degree with a negative leading coefficient, negative LC. It falls on both ends. Okay, and then what happened if I had something like this here? So unlike this, okay. Well, that would be odd degree. It rises on the right and falls on the left. So that would be odd degree, but it would have a positive leading coefficient, odd degree. It would have a positive leading coefficient. Rises on the right and falls on the left. So again, as I said, all you really have to do is remember this here. Remember your quadratics or your cubics and what they look like when the when the leading coefficient is positive or negative. All right. Some other things that would be important here. Okay, so all right. Now we can graph polynomials given the x-intercepts in intercept form. So if a is an x-intercept is 0 of a polynomial function, or x is equal to a, then the factor form or intercept form for a is x minus a. And what that says is exactly what I was talking about when I began the lesson. So here my 0 was x is equal to negative 4. My factor would be x plus 4. Here my 0 was x is equal to 3. My factor would be x minus 3. Here my factors, my 0 is x is equal to 2. My factor would be x minus 2. And here my factor is my 0 is x is equal to 4. My factor would be x minus 4. Okay, so that's what that was saying. If a is an x-intercept, 0 or root of a polynomial function, or x is equal to a, then the factor form or intercept form for a is x minus a. Okay, so here let's try and find the intercept form of these polynomials here. Here my 0 would be x is equal to negative, let's just say negative 2. And here x would equal 1. And here maybe x would equal 2. So those would be my zeros. The intercept form, I could write a polynomial function intercept form. And so my factors would be x plus 2 times x minus 1 times x minus 2. That would be the intercept form of that polynomial. Let me take a look at this one here, the next one. So here I have how many zeros? So let's say here that was x is equal to negative 4. And this was x is equal to negative 3. And then this is x is equal to negative 1. And then here, that's x is equal to 1. And so my polynomial, I could write the polynomial with those zeros in intercept form. It would be x plus 4 times x plus 3 times x plus 1 times x minus 1. Okay, and that would be that polynomial written in intercept form. It would be a degree 4 polynomial. Okay, the degree of each factor is 1. So 1, 1, 1, 1, and you add them up. And so you would get degree 4. For the other one, 1, 1, and 1. You add them all up, you get degree 3. Degree 3 polynomial, degree 4 polynomial. Okay. Oh, I want you to notice something here too. Okay. We say that every polynomial of degree n has exactly n minus 1 bins. So for degree n polynomial, it has exactly n minus 1 bins in the curve. So when I had degree 2, it only been once, or it turned once. Degree 3, it turned once, two times. Degree n, at most n minus 1. Let me clarify that. At most n minus 1 bins in the curve. You can have less, but you can't have more than n minus 1 bins, but you can't have less. When I had degree 4, how many bins did I have? I should have 3. 1, at most 3, 2, 3. at most. Degree 5, I should have at most 4 bins. 1, 2, 3, 4. Degree 4. Degree 5 at most 4 bins. Degree 5 at most 4 bins. Degree 4 at most 3 bins. Degree 3 at most 2 bins. And degree 2 at most 1 bins. I can have fewer bins, but at the most I could have for any n-degree polynomial is n minus 1 bins at most. I can have fewer. Okay, so every polynomial function of degree n will have at most n minus 1 bins or turning points in the graph. So given the x-intercepts of -1, 2, and 2, the factors or the x-intercept form will be x plus 1 times x minus 2 times x minus 2, or x plus 1 times x minus 2 squared. So my polynomial function could be written as y is equal to x plus 1 times x minus 2 squared. That would be a degree 3 polynomial. That would be a degree 3 polynomial. The degree of that first factor is 1. In the degree of the second factor, I have 2 of them, x minus 2, so this would be a degree 3 polynomial. So I should see at most 2 bins in the graph. So I could graph that out. So here's my 0 is -1. And here's my other 2 zeros, 2 and 2. And as you can see, it has at most 2 bins. The leading coefficient is a positive. Leading coefficient is a positive. So remember the x cubed, it looks like this here. Leading coefficient is positive. So that means it rises on the right or falls on the left, or as x goes to positive infinity, y goes to positive infinity. As x goes to negative infinity, y goes to negative infinity. Okay, let's look at another one. Given x-intercepts of 3, -4, -4, -4 with negative leading coefficient, factors or intercept form would be, because I have a negative leading coefficient, so that would be negative. My intercept form would be x minus 3. My 0 is 3, so x minus 3. And then x plus 4. My 0 is -4, so my intercept form or factor form would be x plus 4. And then x plus 4 again, and then x plus 4. Or negative x minus 3 times x plus 4 raised to the third. Now this would be a 4th degree polynomial. 4th degree polynomial. The degree of that factor there is 1, and the degree of the other factor is 3. So this would be a 4th degree polynomial. It would be even. And because the leading coefficient is negative, okay, remember quadratic, sad graph, negative leading coefficient, even degree, it will look like that. Okay, so the graph should point down on both ends. All right, so let's take a look here. So here, I can see that the 0x is equal to -4. Well, there's that 0 there. There's 1 bin. Then the other 0 is x is equal to 3. Okay, so you don't see the entire picture, but that graph kind of looks like this here. It takes a bin here, goes up, and then it comes down. So it's even degree. The degree is 4. And the leading coefficient is negative. Okay, so as x goes to positive infinity, y will go to negative infinity. As x goes to negative infinity, y will go to negative infinity. Okay, I do want you to notice though, it only has 2 bins. Every n degree polynomial would have at most n minus 1 bins. Okay, at most, can't have more. So this fourth degree polynomial can't have more than 4 bends, can't have 4 bends or more. It can have at most 3 bends, but it can also have less than that. Here I only have 2 bends. Every degree polynomial has at most n minus 1 bends or turning points in the graph. So for the fourth degree polynomial, I could have 3 turning points, or I could have fewer. I only have 2 turning points. Okay, all right. So write the intercept form of the given graph. Well, here I see that my 0 is -1, and then 1, and then 2. So polynomial, I can write, well, if my 0 is -1, my factor would be x plus 1. And if my 0 is 1, my factor would be x minus 1. And if my 0 is 2, my factor would be x minus 2. The intercept form. So that would be that polynomial. It would be degree 3. Yeah, so this would be degree 3. And have a positive leading coefficient. And as x goes to positive infinity, y goes to positive infinity. And as x goes to negative infinity, y goes to negative infinity. All right, and then the last one. Okay, so I see that that graph points down on both ends. So it's an even degree, and it has to have a negative leading coefficient. Well, let's see here. My zeros would be, so this is what, -3 and -1. So the intercept form, so that would be x plus 3 times x plus 1. And then my other zeros are 1 and, what's that, 1, 2, 3, 3. Okay, so that would be x minus 1 times x minus 3. So this would be a fourth degree polynomial. The degree of each factor is 1. And so degree 4. And then the leading coefficient. Well, that would be negative because the graph is pointing downwards. So I'd have a negative leading coefficient. Okay. Remember, even degree polynomials, if the leading coefficient is positive, it points up. Positive leading coefficient is, if the leading coefficient is negative, it points down. So that leading coefficient has to be negative because the graph is pointing down. Okay, so there. All right. Now, the last thing I wanted to go over was domain and range. For any odd degree polynomial, the domain and range is just all real numbers. It doesn't matter if the graph looks like that, if it's a positive leading coefficient, or it looks like that, negative leading coefficient. The domain is always all real numbers, and then the range is all real numbers. The graph goes up forever, or it goes down forever, as x goes to positive infinity and y goes to negative infinity. So my domain here would be, in terms of interval notation, negative infinity to infinity, and the range would be from negative infinity to infinity. For even degree polynomials, that's not always the case. Okay, well, that is not the case. Okay, so for example, if I had this polynomial in its even degree, the domain is always all real numbers. Okay, negative infinity to infinity. But the range, well, you have to look at the minimum or maximum value. So for example there, let's say here, so this was what the y value here was, let's say here -4. So the range would be from, the y would go from, like say, -4 to positive infinity. Okay, the lowest value for y would be -4. So that would be the range. And then so that would be, so the leading coefficient of that even degree polynomial would be positive. And this was on your last test. And then if I had a quadratic even degree polynomial that had a negative leading coefficient like that, it would reach a maximum. It would be a sad graph. So let's see here, that y value was y is equal to 7. The domain will still be all real numbers. It would go from negative infinity to infinity, but the range would go from 7 to negative infinity. 7 to negative infinity. Oops. And I guess I should close that, because that would be closed at 7 and this would be closed at negative 4. Okay, so just to review domain and range with you. Okay, so that was an introduction into polynomials. You'll have a lesson on Holt Reinhardt Winston, or Holt McDougall online. I'm sorry, it's no longer Holt Reinhardt Winston. It's Holt McDougall online.